Good afternoon. This hearing is called to order. Since the dawn of time, man has often looked up into the night sky and wondered, what's out there? Are we alone? In 300 BC, the Greek philosopher Epicurus assumed that, quote, other worlds with plants and other living things, some of them similar and some of them different than ours, must exist. The basic question of wondering what lies out there is one that has driven civilizations to risk life and limb to explore not only this planet, but to venture out into the solar system. In 1977, NASA began an effort to try to better answer this question by launching Voyager 1 and Voyager 2, which were originally intended to primarily explore Jupiter and Saturn. Each spacecraft carries a small American flag and a golden record packed with pictures and sounds that are intended to be mementos of our home planet. 40 years after they were launched, Voyager 1 has reached interstellar space, and Voyager 2 is in the outermost layer of the heliosphere, where the solar wind is slowed by the pressure of interstellar gas. As each spacecraft continues on its voyage and transmits scientific information back to Earth, we are left to wonder if the great Steve Martin may still be proven right. That one day we will receive a forward response from intelligent life somewhere in the universe who receive the golden record and simply request, send more Chuck Berry. The search for life isn't just a question of casual interest. It is an integral part of NASA's core mission. In the NASA Transition Authorization Act of 2017, which was signed into law by President Trump, this committee authored and added a short phrase to NASA's mission. Quote, the search for life's origin, evolution, distribution, and future in the universe. The Atlantic has described the addition of that short but momentous phrase as, quote, a visionary one, setting the stage for a far-reaching effort that could have as profound an impact on the 21st century as the Apollo program had on the 20th. Since the enactment of the NASA Transition Authorization Act of 2017, we have even more reason to be encouraged that we're on the right path. Just before our last hearing, the journal Science published a report on radar evidence of subglacial liquid water on Mars. Using radar profiles collected from a satellite between May 2012 and December 2015, scientists have found evidence of a 12-mile-wide reservoir of briny water beneath the South Polar layered deposits. And just 1 month prior to the announcement of this discovery, NASA reported that the Curiosity rover had found new evidence preserved in rocks on Mars, suggesting that the planet could have supported ancient life. We're making progress as we search for life's origin, evolution, distribution, and future in the universe. As we look to draft a new NASA Authorization Act, hopefully this year, it is imperative that we not only continue to make progress answering this question, but that we also equip NASA with the capabilities that it needs to support science missions and priorities that will lead to discoveries across our solar system. This is a momentous time to be involved in space exploration, and I look forward to the testimony of our esteemed witnesses. Now recognize Senator Markey, the ranking member, for his opening remarks.
Thank you, Mr. Chairman, very much. Thank you for having this extremely important hearing today with this incredible panel. Last week, we gained great insight from our witnesses on how Americans will venture out of Earth's orbit beyond the Moon and onto the surface of Mars. Today, we welcome another distinguished panel of experts that will point us in the right direction as we launch science missions into the void of space with the hopes of making groundbreaking discoveries about our solar system, our universe, and our very own home, planet Earth. Currently, NASA's Science Mission Directorate funds space science missions and research in a number of crucial areas, including astrophysics, planetary science, and heliophysics. One of the portfolios within NASA's Science Mission Directorate that is often overlooked, but is absolutely vital, is Earth science, with deadly fires gripping California and Greece, extreme hurricanes in the Atlantic, and searing heat waves and droughts around the world. Our investment in NASA's Earth science and climate research programs and missions must be both abundant and unwavering. NASA's essential Earth observation missions, including the Carbon Monitoring System, the Orbiting Carbon Observatory 2, and the Gravity Recovery and Climate Experiment, or GRACE, give us evidence that the climate is changing. And if we're willing to pay attention, this information can help us prepare for a more dangerous future. We must be sure that NASA's Earth Science program has the resources necessary to provide our scientists with the latest data so that Congress and agencies across the government can combat this problem head-on so that our planet Earth may be home to many future generations to come. And finally, we're very fortunate to have Dr. Sara Seager, Professor of Physics and Planetary Science at MIT, who is a co-investigator on NASA's TESS mission. NASA announced only a few days ago that TESS has been turned on and has begun its search for distant worlds. Carl Sagan once said, "The nature of life on Earth and the quest for life elsewhere are two sides of the same question, the search for who we are." TESS is one of the NASA scientific missions that will help us to find who we are. My colleagues and I have great confidence in the space community, including NASA's team of exceptional scientists and collaborators, and we look forward to the testimony from our witnesses this afternoon. Again, we thank you all for helping us to understand better what our mission here in Congress should be to help you to accomplish this goal. Thank you, Mr. Chairman.
Thank you. Would now recognize the ranking member of the full committee, Senator Nelson, if you care to make an opening remark.
Thank you, Mr. Chairman. And I would point out that the Science Mission Directorate, it's an incredible amount that they do. 30% of the NASA budget is here. And they are operating 60 missions on 80 spacecraft. It's vast. They want to unlock the secrets of the universe. You all have talked about the search for life and improving life here on Earth. And so legislation that we are putting together is to add the search for life's origin, evolution, distribution, and the future of the universe. That's about everything all rolled into one. So this is one of the gee whiz parts of NASA. And it is complementary with the human missions of NASA, because one complements the other. You can't do one without the other. It's going to be a real challenge for us to protect human life going all the way to Mars. We got to get them there faster than we get there now, and we got to protect them from being fried in the process by radiation. But what we will learn in that mission and that development of technology to sustain human life will also complement, and vice versa, the Science Mission Directorate. So it's going to be an exciting time for NASA. Thank you, Mr. Chairman.
Thank you, Senator Nelson. You talk about the danger of being fried in space. Just yesterday, I was mentioning to my staff the old TV ads, this is your brain on drugs, this is your brain with a side of bacon, and they were too young to have any idea what I was talking about. I'm pleased to welcome each of the witnesses here today. We will start with Dr. Thomas Zurbuchen, who is the Associate Administrator for NASA's Science Mission Directorate. Previously, Dr. Zurbuchen was a professor of space science and aerospace engineering at the University of Michigan in Ann Arbor. Dr. Zurbuchen's experience includes research in solar and heliospheric physics, experimental space research, space systems, and innovation and entrepreneurship. He's been involved in several NASA science missions, including the Ulysses space probe, the Messenger spacecraft to Mercury, and the Advanced Composition Explorer. Dr. Zurbuchen received his PhD in physics from the University of Bern in Switzerland. Our next witness is Dr. Ellen Stofan, who is the director of the Smithsonian National Air and Space Museum. I think it may indeed be a federal law that every visitor, and particularly every child who comes to Washington, must go to the Smithsonian's Air and Space Museum. Dr. Stofan is the 7th person to lead the museum since Apollo 11 astronaut Michael Collins oversaw its founding in 1976, and is the first woman appointed to the position. Dr. Stofan previously served as NASA's chief scientist for 3 years, from 2013 to 2016. In that role, she guided the development of a long-range plan to send humans to Mars, worked on strategies to expand commercial activity in Earth orbit, and supported NASA's science programs in heliophysics, earth science, planetary science, and astrophysics. Prior to that, Dr. Stofan served as the chief scientist for the New Millennial Program at the Jet Propulsion Laboratory in California. Dr. Stofan received her PhD in geological sciences from Brown University. Dr. David Spergel is the Charles A. Young Professor of Astronomy and Professor of Astrophysical Sciences at Princeton University, my alma mater. For over 2 decades, Dr. Spergel has worked on the interpretation and analysis of microwave background data to better understand the basic properties of the universe. Dr. Spergel is the co-chair of the science team for the Wide Field Infrared Survey Telescope, more commonly known as WFIRST. He has been involved in many aspects of the mission and has contributed countless hours of work to creating a telescope that will ultimately let humanity see further into the universe than ever before. Dr. Spergel received his PhD in astronomy from Harvard University. And finally, Dr. Sara Seager, who is a professor of physics and planetary science at the Massachusetts Institute of Technology. A native of Toronto, Dr. Seager's research has made unprecedented discoveries and has gone leaps and bounds to expand humanity's knowledge in the field of astronomy. Dr. Seager's research has introduced many new ideas for the study of exoplanets. In fact, she was part of a team that helped discover the first detection of light emitted from an exoplanet. Additionally, she has conducted swaths of research focusing on theoretical models of atmospheres and interiors of all kinds of exoplanets. Dr. Seager received her PhD in astronomy from Harvard University, and I would note, with all these PhDs, I think the senators sitting here are all badly undereducated. And with that, we will have our first witness, Dr. Zurbuchen.
Thank you so much. Chairman Cruz, Ranking Member Markey, Ranking Member Nelson, and members of the subcommittee. The work of NASA science is at the forefront of scientific discovery and innovation. The questions we seek to answer affect humanity on a global scale and focus on our place in the universe. Where did we come from? Are we alone? Questions that are well aligned with the topic of this hearing. Later this month, NASA will launch our next daring mission, which will touch the sun by actually flying deep through its atmosphere. The Parker Solar Probe is the first spacecraft designed to do so and will revolutionize our understanding of the sun's corona and expand our knowledge of the origin and evolution of the solar wind. This mission will also make critical contributions to our ability to forecast changes in space weather that affect life and society's essential technological infrastructure on and near Earth. Parker will join numerous other exciting missions launched in just a few months past. The Transiting Exoplanet Survey satellite, TESS, launched in mid-April, and is NASA's next planet hunting mission, searching for planets orbiting nearby stars. On July 25th, we just heard, it began conducting the first ever spaceborne all-sky transit survey, as it is expected to catalog more than 1,500 exoplanet candidates, including 500 Earth-sized and super-Earth-sized planets. TESS will identify prime targets for further, more detailed characterization with the James Webb Space Telescope and other missions. Also launched in May, NASA's newest Mars lander, InSight, is now en route for a November touchdown. It will join a complement of NASA rovers, lander, and orbiters at the Red Planet. InSight's advanced payload will provide unique information on the interior structure of Mars and thus other planets. Collaborating closely with the Human Exploration Program at NASA, we continue to use the International Space Station as a valuable platform for great science. On June 29th, the EcoStress instrument was carried to the space station by a commercial resupply mission. EcoStress measures agricultural water use in the United States and plant stress around the globe, and will identify drought warning conditions. In fact, there's no program in NASA science that has more direct impact to everyday life than our Earth Science program, as was mentioned. Whether it is developing the tools to predict severe weather or drought, or whether it is to understand the complex interactions of the Earth system, what we learn here affects our lives. For example, in the midst of the 2017 hurricane season, data produced from NASA's Earth-observing research satellites were used to support real-time decision-making and response efforts by FEMA and others. NASA also integrates science and future human exploration goals with regard to the return of humans to the Moon and to Mars. Establishing a new agency-wide lunar discovery and exploration program and leveraging NASA's extensive lunar science experience and data, NASA is jump-starting commercial partnership, innovative approaches for building and launching next-generation sophisticated science instruments, and the development of small rovers that will reach the Moon's surface via commercial landers. With regard to the hearing topic, the search for life, Planetary science provides some of the most exciting views of the unexplored worlds in our solar system. Progress continues on the Mars 2020 rover, which will carry a small helicopter to Mars, a first for humanity. NASA is also planning for a potential Mars sample return mission, a top priority identified by the scientific community in the most recent decadal for planetary sciences. During 2019, NASA will continue development of the cutting-edge Europa Clipper mission to fly by Jupiter's ocean moon, one of the most promising targets for finding life in our solar system. In many ways, NASA astrophysics and planetary sciences programs are working more closely together than ever, examining how habitable environments develop and contribute to the search for life, as will be discussed by the other witnesses here later. NASA is committed to answering the big questions, and it requires commitment to new and challenging missions. In 2021, NASA's observatories will be joined by the James Webb Space Telescope. Webb will be capable of examining the first stars and galaxies to form and will view the atmospheres of nearby planets outside the solar system. Webb's telescope and instruments are fully integrated and performed superbly during testing, and the spacecraft element comprised of the bus and a tennis court-sized sun shield is completely assembled and undergoing testing. In March 2018, NASA recognized that Webb would take longer and cost more to develop than previously estimated due to the issues involving the integration and testing of the spacecraft elements. I established, as a result of that, an independent review board to provide an assessment of the time and cost necessary to complete development. and the IRB provided valuable recommendations which we're all implementing. In conclusion, as we look forward to the future, NASA's science program will continue to contribute to the scientific and technological advancement of the United States and inspire future scientists and engineers to reach for the stars. I'll be happy to answer any questions.
Thank you. Dr. Stofan.
Chairman Cruz, Ranking Member Markey, Ranking Member Nelson, and the committee, thank you for the opportunity to discuss the search for life beyond Earth. As my esteemed colleagues will discuss life beyond our solar system, I will focus on the search for life within our solar system. As a planetary scientist, former chief scientist of NASA, and the current John and Adrian Mars director of the Smithsonian's National Air and Space Museum, there is no other topic that I find as exciting or as fundamental to future discoveries that will one day be highlighted in my museum as this one. All planetary science begins on Earth. Based on our understanding of how life arose here, it requires long-standing, stable bodies of liquid water. Life evolved rapidly once conditions stabilized on the early Earth, which chemical signatures indicate was about 3.8 billion years ago. We know that life is tenacious, diverse, and highly adaptable. Astrobiologists have found life in extreme environments like volcanic lakes, sulfur springs, and the top of the stratosphere. Microbes have been found that live under high levels of radiation or consume toxic chemicals. We find life on Earth nearly everywhere we look for it. Given the commonality of conditions here and elsewhere in the solar system, it is highly unlikely that life is unique to our planet. We know that the building blocks, amino acids, are ubiquitous in the solar system, found in comets, asteroids, and even in interstellar clouds. The next step is to identify environments potentially habitable to microbial life, like those on the early Earth, with liquid water, a source of nutrients, and a source of energy. Within the icy moons of the outer solar system, we have found subsurface oceans. Jupiter's moon Europa and Saturn's moon Enceladus both have liquid water oceans that have likely been stable for over 1 billion years. These oceans are likely enriched by volcanic eruptions from the moon's rocky inner cores, a possible source for both nutrients and energy. Both moons vent their oceans into space in geyser-like eruptions and could easily be sampled by spacecraft without landing. Cassini sampled the liquid erupting from Enceladus during a flyby and found the water to contain salts, silica, and organic molecules, all pointing to a habitable environment. That sample may have contained signs of microbial life, but Cassini's instruments were not designed to detect them. We need to go back to Enceladus and to Europa with better instruments. How will we know life when we see it? Through years of peer-reviewed theoretical research, lab, and field work, the astrobiology community has developed something called the ladder of life, which lays out what to measure and how to measure it. The ladder begins with a habitable environment with rungs for biomolecules, metabolism, and ultimately Darwinian evolution. Thanks to decades of NASA spacecraft missions, we know how to take the next steps in the search for life at Europa, Enceladus, and of course Mars, and eventually Titan. 3.8 billion years ago, around the same time life arose on Earth, a significant portion of Mars was covered in water. Mars remained wet for about 500 million years before it lost its magnetic field, its atmosphere thinned, and conditions became similar to what we see today, a cold, dusty, dry surface bombarded by solar and cosmic radiation. If life evolved on Mars during its wet, early Earth-like period, fossilized microorganisms should be present in surface rocks. That's why it's astronauts, not just the orbiters, landers, and rovers that have gotten us to this point, are required. Biologists, geologists, and chemists on the ground could do more than identify evidence of past life on Mars. They could study its variation, complexity, and relationship to life on Earth much more effectively than our robotic emissaries. NASA could put humans in orbit around Mars by 2033 and down to the surface later in the decade. This is completely feasible and affordable if the agency focuses on the capabilities and technologies required. Putting humans on Mars by 2038, 20 years from now, is not nearly as audacious as landing on the Moon in 8 short years, a task the United States accomplished nearly 50 years ago. NASA has the infrastructure and commercial partners and the scientific and technical expertise, as we demonstrate every day with research groups like those at Air and Space and the Smithsonian Astrophysical Observatory. The problem is extremely well scoped and studied. We only need to accept the challenge. Putting aside the amazing scientific and technological dividends of a Mars shot, consider the incalculable political, cultural, and historical benefits to this nation that came from the moonshots of the Apollo program. This is another extremely exciting moment in human history. We know where to look, and we know how to look. We have the technology to determine if life has evolved elsewhere in the solar system and can easily do so within the next 2 decades. Thank you very much.
Thank you. Dr. Spergel.
I thank Chairman Cruz, Ranking Member Markey, Ranking Member Nelson, and other committee members for the opportunity to testify. My name is David Spergel, and I'm Professor of Astronomy at Princeton University and Managing Director of the Flatiron Institute in New York. While my spoken remarks will focus on NASA astrophysics, my written remarks discuss the broader space science program, and with the Chairman's permission, I request that my written remarks be made part of the record. Our multi-generational program of exploring and studying space is the modern version of the construction of the great cathedrals of Europe. Many of NASA's most important activities, from sending humans to Mars, to the study of extrasolar planets, to understanding the cosmos, are fundamentally centuries-long projects. In cosmology, we've learned that our universe is both remarkably simple and remarkably strange. Nearly a century ago, Dr. Edwin Hubble, working at the Mount Wilson Observatory, began our program of measuring the size and shape of the universe. Today, the Hubble Space Telescope and measurements of the microwave background continue this program. Over the past 2 decades, we've learned that a simple model with only 5 parameters, the age of the universe, the density of atoms, the density of matter, and the properties of the initial fluctuations, describe all of the basic properties of the universe. While successful, this model implies that atoms, the stuff makes up us, makes up only 5% of the universe. Most of the universe is made of dark matter and dark energy. We don't know what makes up most of the universe. Understanding the nature of dark energy is one of the most compelling problems in physics. Both Europe and China are leading missions to study dark energy. When I was in Beijing last year, I was impressed by China's plans to launch a large space telescope off of its space station with its primary focus on studying dark energy. This telescope will have the world's largest space camera and use Chinese military technology to construct a large off-axis telescope. Fortunately, NASA is moving forward with the premier dark energy mission, WFIRST, the top-ranked large space project in the 2010 Astronomy Decadal Survey. It will measure the expansion rate of the universe and the growth of structure to unprecedented precision. WFIRST is meeting all of its technological requirements, is on schedule for a 2025 launch. Astronomers have learned that the solar system is far from unique. Using observations from the Kepler spacecraft and ground-based observatories, they have discovered thousands of exoplanets, revealing a diversity of planetary architectures and a diversity of planetary systems. Shakespeare's line, "There are more things in heaven and earth, Horatio, than are dreamt of in your philosophy," is perhaps our best guide as we can contemplate whether there is life elsewhere in the Milky Way. Just as the exploration of the cosmos has driven telescope design for the past century, the study of exoplanets and the search for life beyond our solar system will likely shape the telescopes of the coming century. NASA's TESS mission, which was launched in April, should soon reveal many new nearby transiting planets. When launched, the James Webb Space Telescope will be able to characterize the atmospheres of some of these planets. WFIRST coronagraph is poised to be the next step in exoplanet characterization. The coronagraph should be more than 1,000 times more sensitive than previous coronagraphs aboard Hubble and James Webb Space Telescope. It will not only be able to image massive planets around nearby stars, but will be the stepping stone for developing technologies for the next generation of great observatories. Understanding planet formation requires using a wide range of observational approaches. Within our own solar system, comets and asteroids are the fossils of the early solar system. Radio and infrared observations reveal extrasolar planetary systems information. And WFIRST will complete the census begun by Kepler and TESS with its microlensing programs. These should reveal thousands of planets in the outer regions of their solar systems. These large projects are challenging and require perseverance. JWST's delays are frustrating to all of us. While the report by the IRB was painful to read at times, I believe that JWST will not only be a transformative astronomical observatory, but will be a flagship of all of NASA, and the eventual success of this incredibly complex engineering project will be a source of national pride and a symbol of U.S. technical prowess. Since JWST is an agency-wide priority, these new costs should be spread across the agency. They are borne entirely by the Astrophysics Directorate. They will have a devastating effect on its future missions and its scientific program. Despite these challenges, this is an incredibly exciting time in astrophysics. NASA satellites have enabled the discovery of thousands of exoplanets, are detecting the optical counterparts of merging neutron stars whose gravitational waves have traveled for billions of light years, and are tracing the large-scale distribution of dark matter and dark energy. Most importantly, each of these discoveries raises new questions that future satellite missions will address in the years to come. The upcoming National Academy of Sciences survey, decadal survey, will provide an opportunity to outline a new vision for the coming decade. I look forward to your questions. Thank you.
Thank you. Dr. Seager.
Chairman Cruz, Ranking Member Markey, Ranking Member Nelson, and committee members, thank you for the opportunity to appear today. I open with a quote from one of our founding fathers, John Adams. Quote, "Astronomers tell us, with good reason, that not only all the planets and satellites in our solar system, but all the unnumbered worlds that revolve around the fixed stars are inhabited." So it's amazing that even then, they believed that there was life everywhere. Although we don't have evidence for life beyond Earth, we are the first generation with the capability to find it. We do know for certain stars are suns. We know of thousands of planets orbiting other stars called exoplanets. And as we've heard from the other witnesses, we have a growing list of solar system bodies with evidence of subsurface liquid water, including Mars, Europa, Enceladus, and others. And because water is required for all life as we know it, these bodies might be able to support life. We heard also from other witnesses that TESS, NASA's new planet hunting mission, it's an MIT-led all-sky survey. It launched on August 18th. It started science operations July 21st, and actually next week and in August, it will be delivering the first science data to Earth. As Deputy Science Director, my team is ready to go, and I thought you might appreciate knowing that finding exoplanets today is, at least with the method TESS uses, is actually standard operating procedure. TESS, in part, aims to discover the best planets for follow-up with the Webb telescope, and its Webb's large collecting area, infrared capability make it suitable to observe exoplanet atmospheres. I just want you to know that despite the delays and cost growth, the exoplanet community is tremendously enthusiastic because Webb will provide our first capability to study exoplanets in the search for life. Webb will observe a small number of prized exoplanets, looking at their atmospheres for gases that might be attributed to life. On Earth, oxygen's the best example, because without plants and bacteria, our planet would have no oxygen. The planets the TESS-Webb combination will find and study, it's not like Earth or our sun. It actually is limited to planets orbiting red dwarf stars, because it's easier to find and study planets around small stars compared to relatively large stars like our sun. These planets orbiting red dwarf stars may be very different from Earth because the red dwarf stars give off giant bursts of energy, flares, and ultraviolet radiation that would frequently bathe the planet's surface. We actually had an event like this in the 1850s, and just as an aside, we're worried that may happen again here because of the power grid, but on these planets it would be happening daily. It would disable, if we humans couldn't tolerate it because it would ruin electronics, like using our cell phone. It would disable the power grids and even destroy our biological cells. But we're hopeful that life that evolved there would be naturally adapted to those conditions. So the ultimate goal is to find a true Earth twin, one orbiting a star like our sun, whose environment we can understand in the context for the search for life. And the huge challenge, actually, is that an Earth-like exoplanet is next to a big, massive, bright star like the sun. And the difference in brightness between the two is 1 part in 10 billion. So we need a way to block out the starlight to 1 part in 10 billion to see the planet directly. The WFIRST coronagraph instrument is the first high-contrast space-based coronagraph. It has specialized optics to block out the starlight to study exoplanets. CGI is a technology demonstration, so it won't be able to reach down to find other planets like Earth. It can study about a dozen giant exoplanets that are already known to exist. It's actually critical to do this technology demonstration to buy down risk for the future for large NASA missions, more ambitious missions already under study. We do have a technique to reach down to find Earths with a modest-sized telescope called Starshade. Starshade is a giant, specially shaped screen, tens of meters in diameter, with its own spacecraft, and it would fly information with a telescope tens of thousands of kilometers away. The Starshade does all the hard work of blocking out the starlight, so only planet light enters the telescope, and technical reasons behind that are why the Starshade can already find Earth analogs, even with a modest-sized telescope. The Starshade builds upon large radio deployables, large space-based radio deployable antennas. NASA has a directed effort to mature Starshade technologies by 2023, though it could happen sooner with more funding. A Starshade with WFIRST would be the first mission opportunity with the ability to discover dozens of new exoplanets, and the first chance we have to find a few planets like Earth. The concept envisions a Starshade launched shortly after WFIRST to rendezvous with it on orbit, and NASA has directed the WFIRST project to be operational with the Starshade, with costs borne by the WFIRST project through 2020 and later by the Starshade project, pending a decadal survey recommendation. There's more details there, but short on time, I'll move on to just tell you that, so I'm proud to tell you that in 2010, I became a citizen of the United States of America. And the reason I came here to work at MIT and be here is because we are the world leader in space technology. And we have some tough priority choices ahead if our nation is to be the first to discover signs of life beyond Earth, whether that's on a planet in our solar system or signs of life on a distant exoplanet. Mr. Chairman and committee, this concludes my remarks. Thank you for your attention and for your continued support for NASA's space science missions.
Thank you very much, and thank you to each of the witnesses. Let's start out with a question to all four of you, which is, why should we be engaged in the search for life? Why does it matter? And why should that be a priority for our space mission?
I believe it's one of the big questions of all of humanity. This is how great nations make a mark. It's by what they do for their citizens, but also how they move history forward. This will be one of those questions, if answered, that will be remembered forever, because it will be a leap in not only understanding more about nature, but a leap in understanding ourselves at a level we've never had in the past.
You know, since Thomas gave kind of the underlying philosophical answer, which I 100% agree with, I would probably like to focus on, you know, when we try to do things that are really hard, like we did at the time of Apollo, when you push yourself to answer the really tough questions, that's when you really push technology forward. And I would argue when you push technology forward, you push your society forward, you push the economy forward. So trying to answer these big questions, building big telescopes, sending humans to Mars, these are an investment in the future of our country, and I think that is critically important.
Let me just add another element which I see as a professor and working with students, which is this is a question that I think engages everyone. This is a question that kids in elementary school, when you go talk to them, ask about, and certainly something that college students are engaged with. And by asking this question, we draw people into science and help bring in this next generation who will be part of our STEM education community. And so I think this is another one of the side benefits. You know, while many of us do this because we want to know the answer, but we have these benefits that come from exploring these questions.
I'll add on to that, and then I have a second one. So most senior engineers today, either in civilian space science or in national defense and national security, they were inspired by the moon landings. And today, the equivalent of that is the search for life. And that public search, and when we do discover it, will inspire that next generation to go into technology. Secondly, just for the record, it takes a ton of pure science research to come up with anything practical, things you could never invent if you set out to find something practical. Like a relevant example is GPS. We all rely on it. But it didn't come because someone said, hey, I need a navigation system for my car. So it turns out that just by exploring, we do have unique practical spin-offs.
Thank you. Dr. Spergel, you previously tweeted, what is driving the acceleration of the universe? What are the properties of exoplanet atmospheres? How did our galaxy and its neighbors form and evolve? What determines the architecture of exoplanets? U.S. should be leading the world in addressing these big questions. Is the United States right now leading the world in addressing these big questions? And what do we need to do better to ensure that we are and remain the global leader?
I think we are leading the world in addressing these questions at the moment, but looking around the world, I see both excellence coming out of our European colleagues. The European Space Agency is launching a number of space science missions that are pushing the edge forward. Their Gaia mission is giving us new insight into galactic dynamics. They've certainly are at the cutting edge in areas like astrometry. They're often partnered with us in many of the projects. And looking east, I have been very impressed by the investments that the Chinese are making in space science. They were really not even significant players 10 years ago. Looking to where they might be a decade from now, if we stop investing, they will be the leaders.
I'll just add on to that about China.
Unfortunately, the technology is finicky.
Okay, so we used to say that China can copy perfectly but not innovate, and now that might be changing, and they're pouring a ton of money into everything, ranging from like solar panel technology to nuclear power to space. And so we have to sort of, it sounds trite, but we want to maintain our healthy budget here for innovative science.
So this committee is working on a new NASA authorization bill. We passed one last year, the first one that had passed in 7 years, and we're working on yet another one that I hope we will pass this year. Let me ask the witnesses, what do you see as the science-related priorities that are most important to be reflected in that bill?
For me, and I'll put on my hat as former chair of the Space Studies Board, what we try to do with the decadal surveys is identify what I think are the top scientific priorities in each of the areas that NASA Science Mission Directorate works. So in planetary science, it has certainly been the top priority to go to Mars, return a sample from Mars, and to explore, followed by exploring Europa. In heliophysics, understanding the processes of the sun, space weather. In astrophysics, completing JWST and then WFIRST would be the current top priorities. We're about to engage in the astrophysics community in our process of looking at the proposed missions and identifying the next set of priorities. I think we'll begin by thinking about what are the key driving questions. The search for life will almost certainly be one. Others will include understanding the processes of galaxy formation, star formation, and the emergence of structure. And of course, in earth science and space, as Ranking Member Markey mentioned earlier, understanding the Earth and using the vantage point of space to watch the changing environment is another key part of NASA's mission.
Chairman Cruz's remarks. It's yours, because mine. Oh, Chairman Cruz's remarks started with the Greeks and the planets, and I think a priority should be finding the true Earth twin orbiting one of our nearest sun-like stars. And that's a very hard problem, 1 part in 10 billion. But it's something that America is leading the way. The Starshade, for example, is not being developed in any other country.
Thank you. Senator Markey.
Thank you, Mr. Chairman. Again, we want to search for faraway planets, but we also want to make sure that we do our work here on Earth correctly. And NASA has been a leader in climate science in helping us to understand where we live, and gives us the most up-to-date data and projections with missions such as OCO2 and GRACE. So, Associate Administrator Zurbuchen, is NASA's Earth science research important to understanding threats like climate science?
The
Climate
Earth Science
change.
Program is a very important program for the nation. The Earth Science Program that we have is very strong. We have, an increasing number of spacecraft in orbit. I think last time I counted was 17, missions on orbit and several in development. And yes, I do believe that this very important program and unique program, complementary to other efforts that are going on within the government and beyond, is very important for NASA and the nation.
And will you make a commitment to this committee that Earth science will remain a priority for NASA in the years ahead?
The Earth science as a key element of NASA has been with NASA from the very beginning, and I'll make a commitment that we will implement everything, the program that's being appropriated here, and that includes, as you know, a strong Earth science program, and in that sense, absolutely yes.
Okay, so let's go down and have each one of you give us an example of how deep space exploration relates to or helps us back here on Earth. Okay. Can you give us an example? You know, we had GPS earlier given to us as an example from earlier space exploration. So how would it relate in the 21st century to each of us in terms of the breakthroughs that are possible?
You know, one of my favorite examples has always been back to this issue of climate, of how do we really understand this planet's climate? And when you put it in the context of saying, looking at Venus, looking at Mars, looking at Saturn's moon Titan, we actually have other bodies in the solar system that have varying amounts of carbon dioxide. They have different greenhouse gases. And so by understanding the climates of not just Earth, but being able to compare the climate of Earth to other planets, it has helped us to really understand what is happening here. And in fact, we actually first identified the ozone hole on Earth after it was a scientist who'd been looking at Venus, came back and looked at the Earth, and that was how that problem was actually first identified.
Uh-huh. So that's how Mario did that? Interesting. Yeah. Dr. Spergel.
Another example that comes to mind is studying ice planets and then looking at glaciers. And it's, you're looking at the same physics. And the remote sensing technologies, ISAT-2 is launching, I believe, in September. And we use many of the same remote sensing technologies when we go visiting planets in our own solar system as when we do looking back on Earth. And one of the things that we see often in science is if you look at one example, you don't fully understand what's going on. We've understood the Earth much better, and as Dr. Stofan mentioned, we've understood processes on the Earth by first observing things that are happening on Venus, on Mars, elsewhere. And now when we look at extrasolar planetary systems, we're understanding our solar system better, because we now see our solar system as but one example of many. And stepping back and getting this bigger picture and understanding those physical processes makes us rethink the way we think about the Earth.
Great. Dr. Seager.
Well, medical imaging is one we're all familiar with. Many people get MRIs or other scans. In astronomy, we have to do the same thing, process data that we get from the sky, and medical imaging can thank astronomy techniques for making big leaps forward. I have another brief one, is that my team, first at MIT and Draper Lab and then at Jet Propulsion Lab, we built a little CubeSat, a small telescope in space to find planets. What it does, new in technology, is it can point precisely, more precisely than, 100 times more precisely than any time in its mass category. Will its legacy to be find exoplanets? Probably not. But the people most interested in it come from optical communication, a way to pack more information than at radio waves, and that's probably where the technology will end up being used.
Great. Dr. Zurbuchen.
You know, one of the things I've been personally involved with in my past, before I took this job, is in some of the spin-outs that came from developing space technology, including electronics that were developed to study some environmental conditions on Mars that are now routinely used in manufacturing environments to prevent discharges from happening, and many others. So there's so many, we could talk here for hours.
Okay, great. Thank you. Thank you, Mr. Chairman.
Thank you. Senator Hassan.
Well, thank you, Mr. Chairman and Ranking Member, for holding this hearing. Thank you to all of our witnesses today. It is a real pleasure to see you all. I would like to offer an especially warm welcome to Dr. Stofan, because she, like I, is a Brown alumnus, so thank you. And it's also, I'm glad that the chair recognized you as the first woman director of the museum. It's very important for girls and young women to see women lead in science. So for both you and Dr. Seager, and having a 50-50 panel here is kind of a nice visual. Dr. Zurbuchen, I'd like to just start with you and to touch a little bit on space weather. Dr. Harlan Spence leads the Institute for the Study of Earth, Oceans, and Space at the University of New Hampshire, my home state, and he's a world-renowned expert on space weather. He leads a research group that studies the physics of cosmic plasmas, from the sun's corona to interplanetary space to Earth's upper atmosphere, using experimental and modeling techniques. This research will ultimately help enhance our understanding of the potential threats space weather can present to Earth, among other unique discoveries. That's why investing in space weather research is so critical. So, Doctor, is NASA providing the resources needed to implement the National Space Weather Action Plan and National Space Weather Strategy?
We have started with the last 2 or 3 years of investments that followed the plan. We have started to implement some of these recommendations. Not all of them are fully funded at the level that were initially foreseen, and there's a number of discussions that are happening, as you know, across agencies of how we best do that. For example, we're coming up with innovative ideas to actually get space weather data from L1 in a collaboration, a unique collaboration between NASA and NOAA that was not initially foreseen. So it's that level of discussion that we're having as we go forward and actually really come up with a full implementation of this action plan. So yes, we're on the way. Could we go even faster? Probably.
Well, that's helpful. I note that, as I understand it, NASA funds science missions based on priorities set by the National Academies of Science, which makes a lot of sense, but there are obviously other, maybe we refer to them more applied reasons to fund space weather research. So how should NASA go about balancing, pure science priorities on the one hand and national needs on the other when determining what research to fund?
I think that's a really important question, and one that I think about a lot in the context of both Earth science, also planetary science in the context of planetary defense. These objects that are hurling through space that can potentially affect human life on Earth, and also space weather. In this case, what's actually interesting is that the entire community is really deeply embracing space weather, and the reason I'm saying that is if you go back to the last decadal, which is really the guiding document of this, space weather is an important part of the entire program, and actually has its specific set of recommendations that we're following at the same level as the others. So what we're trying to do also in this case is wherever we get such guidance from the science community, implement that, of course, with all the constraints and overarching policy guidance that we're getting from here or elsewhere.
Would anybody else like to comment on striking that balance?
I'll say that we probably don't have a good answer for you, unfortunately. We're unfortunately bound by these decadal surveys. And you're right that it is really a science priority, not a national needs-based priority.
Okay. Dr. Spergel?
Though I think there'll be another heliophysics decadal coming up reasonably soon, and having been involved in the process, things like if NASA instructs the Academy to weight those priorities in the evaluations, that becomes part of the process.
Okay. Thank you.
Yeah, and I would just add the whole, NASA has a whole earth science, applied sciences area where they're doing critical work to support farmers with drought information and crop information, and I think that balance is really important and really critical, and in the earth sciences, I know this is top of mind.
Well, thank you. And I just wanted Dr. Stofan to touch briefly with you, and maybe we can follow up in writing, but I've seen your remarks recently on the importance of diversifying the workforces that make all of these critical scientific achievements possible. Can you just comment on how important it is that we invest in our nation's children throughout their early education, as well as through collegiate and postgraduate studies, to ensure that we have a pipeline of people like the four of you who can carry on this important research and make even greater strides for American space exploration?
If we don't focus on increasing diversity in science, technology, engineering, and math, we are doing a disservice to our country because we are not tapping into the talent of all of our population. So to me, it's not just something nice to do, it's something that we have to do, and it's something we focus on at the Smithsonian, and to me, that's one of the things that I hope to do at Air and Space, is really focus on telling those diverse stories, as we do across the Smithsonian, to really inspire that next generation to be the innovators and explorers.
Well, thank you very much, and thank you, Mr. Chair.
Thank you. Senator Peters.
Thank you, Mr. Chairman, Ranking Member. Thank you to our panelists for discussion. And Senator Hassan, I just want to thank you, too, for bringing up space weather issue. It is a very big issue, one that the University of Michigan folks are very involved in as well. And I think, as some of the panelists may know, is why we've passed the bill that I worked on with Senator Gardner, the Space Weather Research and Forecasting Act, which has passed the Senate now twice. It just came out of a House committee recently. Unfortunately, I think it was weakened as it came out of the House. We're hoping to strengthen that to make sure that we get everybody on the same page when it comes to forecasting these weather events, which can be extreme. Dr. Seager, I'm going to ask you to talk a little bit about that. I mean, my understanding is that our space weather forecasting abilities are similar to our abilities to forecast hurricanes in the 1930s, okay. Which wasn't all that great in the 1930s. We've gotten a whole lot better. But if we see an event like you mentioned in your testimony, the Carrington event, I think Lloyd's of London has estimated that's well in excess of $1 trillion impact on our economy. This is significant. We haven't been acting quick enough. I don't think there's been enough coordination, which is part of the act, is to make sure that this is not just science, it's the homeland security and defense, all sorts of issues related to it. But would you tell us exactly why it's so important that we get going on making sure that we have space weather capabilities?
Well, I'm not an expert on space weather forecasting. I do know, I see the Carrington event like the earthquake in San Francisco or Los Angeles. We're all waiting for the big one. And when it comes here, I think it's not just space weather forecasting, but as you say, also how we're going to protect our satellites and power grid.
Anybody else? Dr. Zurbuchen?
So, you know, space weather is one of those one of those elements of our research program in many ways. If your esteemed faculty members sat here would say the same thing. It's like one of those, frankly, when I did my grad school, it was not as prevalent as we are thinking about it today. And the simple reason for that is we're way more dependent on space than we were 20, 30 years ago. And so this is becoming much more important. Yes, we have made strides towards this. Are we going at maximum speed possible? Probably not. We're seeking to do the best. If you look at the 2019 budget, you see increases in some of the areas that we're requesting to actually accelerate some of the work that's, of course, under consideration in this building and others up here. And so, yes, we seek to, respond to the desire that you're talking about, Senator, because we see the importance in a direct fashion.
And my understanding, it's not a question of if we're going to have a big event, it's just when. And we're past due for that event. And my understanding is if you do see a blackout of grid and the big transformers that control that are burned out as a result of that, you could see outages for 6 months to a year. So just folks who may read the transcript of this hearing, just think of New York City without power for 1 year. That would be catastrophic for our country. So this is an investment that we need to be making and doing it in a thoughtful way.
And just tying back to the question about what practical come out of space exploration, this may be our best example.
Right. Thank you. Dr. Stofan, you mentioned the life on Mars and the possibility for that. Just a question. You said that basically you're looking at water-based life, and Mars had water for about 500 million years. That seems like a fairly short time, given how long it took on Earth. Why are you confident that that's enough time that we might be able to find something there?
Well, because remember, actually life arose rapidly here on Earth once conditions stabilized. So, the first several 100 million years on Earth, conditions were pretty hostile. It was really as soon as conditions stabilized, within 100 million years or so, we're fairly confident that the first microbial life evolved on Earth. So the problem is life remained in the oceans for over 1 billion years, and it took well over 1 billion years for life to gain any complexity. That's why I'm optimistic that life did evolve on Mars. I'm not optimistic that it got very complex. So we're talking about finding fossil microbes, so single-celled organisms, blue-green algae type thing, so hard to find. And that's why I do think it will take humans on the planet breaking open a lot of rocks to try to actually find this evidence of past life. And finding one sample is not good enough. You need multiple samples to understand the diversity.
You brought up finding complex life, and we've often been intrigued by the idea that there might be civilizations out there that can communicate with us to be advanced. There are some that argue that we should have probably already found that if it exists, and the fact that the Earth is 4.5 billion years old. The universe is 14 billion, so you could conceivably have civilizations that have been in existence for 1 billion years. They would be very advanced. When you think about how much advancement we have had now, are we searching? Are we confident we're searching in the right way for civilizations that may be so far advanced and may not be communicating the way we do? How do we even know that? This is a broad philosophical question, but I think is one we have to be thinking about if we're putting resources into probably the most intriguing question of life on another planet.
I think we are heading down the right path, and that is to build upon, while we're looking for exoplanets around other stars, we're trying to understand the nature and variety of life that might have evolved in our own solar system. I think once we start realizing how common life is in this solar system, it gives us a better basis. And once we start gaining data on exoplanets, their surface conditions, it gives us a basis for which to start thinking about how likely is complex life, where should we go to find it. And so I think we need more data, and so I think the way we're approaching the problem is absolutely correct.
Right. Thank you.
Thank you, Senator Peters. We'll do a few more questions. Let's start, Dr. Zurbuchen. The James Webb Space Telescope, the successor to the Hubble Space Telescope, is meant to revolutionize the world's understanding of planets and star formation. As you know, the telescope was initially expected to launch in 2007 and cost roughly $500 million. That cost skyrocketed to $5 billion by 2011, and now is delayed until 2021, with cost expected to surpass $9.6 billion. What explains that incredible increase in cost and delay in deployment?
That's the question I'm asking myself and my team on a regular basis, and I can tell you what I think, what we have concluded already, or we think are really important questions. That I think it's more than one issue that affects that. The first, I would say, is excessive optimism. By the way, innovators need to be need to be optimists. You never start if you understand how complex the challenge is ahead, but excessive optimism can be trapping you into path that you will regret later. And so for us, what that means for me as a leader and as a manager, I want to build in mechanisms that actually look at this, such as independent reviews of the type we did with WFIRST that David talked about earlier, to really get our arms around it. The second one, I would argue, is the confluence of something like the development of something like 10 new technologies. Every new technology by itself is hard to guess how long it will take. 10 together is much, much harder. It's not 10 times harder. It may be 50, 100 times harder because these technologies interact with each other. So for me, what that means is when I look at missions now, I want to understand how many technologies really are there and try to understand whether we can actually develop these technologies before we lock in cost. And then the third one, I think we're learning now, and the thing that led to the increase in cost that you're referring to relative to the independent review board has to do with really closing off at the integration and test level the work that we're having there. And so what we're finding are, are challenges related to just doing the work and avoiding the impact of human errors and embedded problems that really have led to increases in cost. That relates to just really how we manage, our processes, and really make sure that our processes are absolutely clear and that we also understand the culture of the workforce and at many places where this happens. This is not just all done at NASA's, it's done in the entire contractor community. So those are, I would argue, the three kind of prime reasons and the lessons we learned from the three.
Have these massive cost overruns caused NASA to reassess the effectiveness of cost-plus contracting for big projects like this?
Yes, we're talking about different type of contracting vehicles in a variety of ways. And in new innovative projects of the type that nobody has ever done, it will be very hard to get a fixed price contract from a company. And having been a board member on some of these companies, you'd want to understand why the CEO wants to do that, right? So basically for us, it's a matter of trying to understand where the right balance is between, a fixed price contract, which of course protects the government from new learnings. And frankly, we have some of these fixed price contracts, and they, in some cases, the company may regret that. In some cases, that's a good thing for them, which is we hope, right? In a cost-plus contract, what it allows us to do, of course, is to manage as we go forward, as we learn and kind of learn new things, to actually really interact with that company and kind of redirect them, if you want them, towards a more optimized path. And so for us, yes, we constantly look at the procurement vehicles we have and try to also understand whether there's even new ones, such as services contracts of the type that we're using in the lunar program, which is totally different than anything else, and then there's some risk with that too, because it may very well be that some of these companies may not be ready. But yes, we're absolutely looking at those.
Let me shift, Dr. Zurbuchen, to a different topic, which is that your written testimony states that NASA maintains a vigorous planetary defense program, which includes the Near-Earth Object Observations Project. As you know, earlier this year, on April 15th, an asteroid named Asteroid 2018 GE3 that is estimated to be at least 150 feet in diameter was spotted about 119,500 miles from Earth, a distance closer than the Moon is from Earth. What do you see as the greatest challenges that our nation faces as it pertains to planetary defense from asteroids, and what step do we need to be taking so that we don't have to rely on sending Bruce Willis to space to save humanity?
I like that movie.
Me too.
What we have done in the 2019 budget proposal is we proposed that we create an integrated program that actually takes advantage of all data sources, including from tests and other kind of spacecraft that are out there, to go look for these bodies. We want to integrate that and basically get a real inventory of what's out there that's a threat of 140 meters and above. Now, there are certain parts of these data where we're always going to be weaker if we're observing from Earth. And what the strategic plans have done is actually proposed that we need to go away from Earth, because frankly, you can't observe things coming out of the sun. It's because it's bright, right? And so you can't see these bodies. And so for us to get that inventory, we probably will have to have an asset that we currently don't have, that is away from the Earth and can look back. Once we have an inventory of this, I think the next will focus on really mitigating these threats. I mean, it's understanding all the threats and mitigating the threats, and depending on the size, the mitigation tools are different. We have one mission, the DART mission, that we're currently working on, which is one type of mitigation, an impact. So we basically ram a spacecraft into a body like this to give it a bump that in a target would bring it out of a collision zone, so to say. So it's those two challenges we're focusing on, or propose to focus on in this integrated program.
Okay, and last question. In addition to NASA's incredible leadership on space exploration and science, we've also seen tremendous cooperation and collaboration with the private sector. Can and should NASA be doing more to utilize commercial partners and utilize private capital as it pertains to the agency's science priorities?
Why don't I start with that answer? And we are continually assessing this, and kind of the way we're doing it, frankly, is to run experiments. For example, we're close to finishing off a commercial data buy from constellations of small spacecraft. That would provide a new way of getting data into the Earth science community in ways that we don't even build the spacecraft, that some companies may be better, cheaper at building some of these spacecraft. Not all data, but some data that we may be able to do. The services contracts is, of the type that we're using with Lunar, and there's several others. Hosting payloads on commercial spacecraft. We have 3 that are currently in our program. So each one, we're running a variety of experiments like that to really see what's there, and continually, our commitment is to continually do that, to really make sure that we can offload things that the private sector can do to the private sector. It's not our intent ever to compete with the private sector. Our intent is to grow that sector and benefit from positive partnerships to really offload things that are possible there, so we can focus on the bleeding edge of the type that, Dr. Seager and others have talked about.
I'll just add to that and say, SpaceX, and he may be talking about Planet Labs, like the seed of innovation is in private commercial industry because they can afford to take risks that NASA cannot. So it's definitely the way forward.
I think the ecosystem of potential partners has gotten much bigger. It's not just the aerospace companies, but there's areas like robotics. 20 years ago, I suspect that NASA represented a significant fraction of all work in robotics. Today, it's a tiny fraction, with enormous amounts money going to things like self-driving cars and, of course, things in factories. And I think there's an opportunity for NASA, I know they're doing their best to take advantage of this, to partner not only with the Boeings and the SpaceXs, but many small companies that are growing in sectors like robotics, computer science, machine learning, and so on.
Yeah, and I would just add that I think it's really important for NASA to stay focused on what only NASA can do. And that, to me, certainly hinges around things like building the next giant telescopes, focusing on making sure we understand this planet, and getting humans to Mars.
Thank you. Senator Markey.
Dr. Seager, I want to talk about NASA's mission prioritization process. We only have so much money. There are many missions. Are you satisfied with the prioritization process that they have at NASA?
I think it's a question worth asking to everybody. We have the decadal surveys, but
I'm going to start with you,
okay.
And then I'm going to go down the rest of them.
Okay.
But because you're from Massachusetts, I thought I'd start with you. But I do want to hear from each of the rest of the witnesses as well.
Sure. Well, you've heard many times how the witnesses always go back to the decadal survey. And it's kind of this structure that we're, let's say, forced to abide by. But I want to say that any institution, any kind of structure that's been around for more than half a century, I think it should be reviewed to see if it's still effective. Maybe it has been reviewed already, but I think it's really time to take a better look at it. I think there's many areas, room for improvement there, which I won't go into now.
Okay. Well, why don't you give us one example of improvement?
Sure, I'll give you one, because in many areas of space science, so we have the James Webb Space Telescope, it's a good example, as is WFIRST and other missions, that the whole community feels that if they don't have one mission that the entire community buys into, that it will never get selected by the decadal survey. So what this means is that the community wants to put forward missions that are very complicated, like it had 10 new technologies. And the question is, are we at a place like of maturity in space technology now where we should have more focused missions that are also big missions, but not try to do everything in one place? And we can't really do that in the current formulation of the survey. We also had this other comment about the younger people not knowing about, well, sometimes the younger people know more. They're the first to use, Instagram and do new things, but also the way that the hierarchy of the survey is, the top panel is senior esteemed people who don't necessarily wouldn't necessarily vote the same way the new generation would.
Right. And again, the kid who came up with Instagram is a high school kid from Hopkinton, Massachusetts. So you are right. Dr. Spergel.
So the decadal process has been an effective way of making prioritizations, and it's a process that can and is being improved. In fact, the Academy, with responding to a NASA request, actually looked at the decadal process as a whole. One advantage of doing things many times and doing it for multiple communities, astrophysics, heliophysics, Earth science from space, planetary science, is you can look across the different communities and see when did the process work best, when were mistakes made. I think one of the mistakes that have been made in the past, and to go back to JWST, is we did not properly study and cost something before the recommendations were made. I think that if we were to go back in time, James Webb will be great, but I think we would have preferred to be able to build a 4-meter James Webb Space Telescope that would have launched for less money a decade ago and do other things. And one of the lessons learned is missions going into the decadal survey don't go in as vague ideas on PowerPoint. They are studied extensively beforehand. And I think one of the investments that NASA has been making leading up to the 2020 decadal, and I think it's important to do for the other decadals in other fields, is that potential missions are studied. So when they are prioritized, we know what we're looking at. Ultimately, this is a cost-benefit analysis, and we need to have at least a preliminary understanding of costs.
Okay, beautiful. Dr. Stofan.
Yeah, I was involved in the last 2 planetary science decadals, and also as I was chief scientist at NASA watched the Earth science decadal going forward. And I saw the process being hugely reviewed and given a lot of thought on how to improve it. And I think it's an important and strong process that needs to be adhered to because it really allows the best science to come forward. It's not the person who shouts the loudest or has the most connections. It really is the best science. And to me, that allows the U.S. to then retain our position as leading in so many of these fields.
Well, how do you correct that so that the people who yell the loudest and have the stake in the biggest project don't win?
Well, I think in the planetary science and in the earth science, I saw that happen really well, where you had broad input from the community. There was input that was sought from across the scientific community, that it was argued out in many small panels, argued out in larger panels, and I thought the process actually—
So you're happy with the prioritization?
I'm happy with the prioritization.
Interesting. Okay, Dr. Zurbuchen.
I have to tell you that I'm really glad that I'm not in charge of science prioritization. And the simple reason is I would not know how to do it in the absence of a framing activity that involves many voices in different ways. For me, like the decadal has been a very successful activity, but like every human endeavor should always be questioned and should be improved as we go forward. I actually resonate with what Dr. Seager's comments the comment she made is like, for example, it's really important that in these panels, a diverse set of opinions are being listened to. And because that's where good decisions come from. You know, people from different type of backgrounds with different kind of priorities, for example, some that also have been in the private sector and actually understand that interface. It's really helpful. Now, in some of this, so that's really important. I agree with her. So we should, as a community, continually go question whether we're doing it the right way. But overall, I'm really happy we have this. I don't know how I could do the job without it.
Great. So anyway, thank you all for your service to our country and to the planet. Thank you.
And I want to thank each of the witnesses for being here, for your testimony. I think this hearing was helpful and productive, and your expertise is what made it so. The hearing record will remain open for the next 2 weeks. During that time, senators are asked to submit any questions for the record, and for the witnesses upon receipt, I would ask that you respond with written answers as soon as possible. And with that, this hearing is adjourned.